think it works. Thank you. So the agenda for today will be, first we'll tell you about our use case, then we'll tell you a little bit about how noise protocol works, and we'll finish up with how exactly we combine noise protocol and the remote attestation. So to start our presentation, our use case is Project Oak. And this is a research project aimed to make it possible for users to reason about how their data is being used on the server side in a way verifiable by external reviewers. And we do this by implementing the following building blocks. We have trust execution environments, remote attestation, and also transparency. So the code is open source, and external reviewers can see the code and basically review it. And there was a great talk by Katsiaryna on one of the OC3 conferences. Please feel free to check it out for more details about it. So the specific use case we're going to focus on today is Oak's restricted environment. In Oak, we are trying to make the job of external reviewers as easy as possible by minimizing the size of the trusted computing base, or TCB. And for this, we have implemented a restricted environment, which contains our custom firmware and our custom kernel implemented in Rust. And the main idea is to minimize the size of the TCB. Another reason why we implemented this restricted environment is because of how remote attestation is done, you get the measurement of the initial memory layout of the VM when you get remote attestation. And if you run generic Linux, after it has started, it can change. And basically, the remote attestation that you get may not correctly represent the current state of the VM. So this is why we implemented restricted kernel, which forces you to only run the code that is attested. But you can get more details about this environment in Conrad's talk on one of the OC3 conferences. OK, so the remote attestation that we provide to users uses DICE. And by DICE, we provide the complete view of the server workload in the following way. We load the first binary into the memory, then we load the second one, and the second one is measured and signed by the first component, and so on. So in the end, we end up with a certificate chain containing all of the measurements of the binaries that run inside the VM. But if you want to get more details about this, there is yet another talk from OC3 conference that we already had in the past. But today, we want to focus on how exactly we implemented end-to-end encryption between the client device and the CVM. And because we have such a minimalistic use case, we also wanted to have a minimalistic crypto protocol that we can use to bind it together with the remote attestation. And technically, because we already provide remote attestation, we didn't need to have PKI, and we didn't need to have certificates. Another feature that we wanted is to minimize the amount of parsers that are in the code. Because parsers are often very tricky parts in which external reviewers has to spend the most attention. Because there could be multiple vulnerabilities in those, and they have to look out for them. And also, because we like Rust very much, we also wanted to have a Rust-only implementation. And our protocol of choice was the noise protocol. So what is noise protocol? Technically, it is a framework for building simple crypto protocols. And the main idea is that it is directly based on the Diffie-Hellman key agreement. So you don't need to have certificates or certificate authorities. Another nice feature is that it doesn't restrict the wire format for you. It just provides you with bytes, which you can incorporate into your own protocol. And it also allows you to have optional authentication, and we needed this because we already provide remote attestation. So the way you can construct new crypto protocols with noise is by using patterns. And patterns define which keys are used by the protocol and in which exact order. And noise has two types of keys, ephemeral keys and static keys, which are long-term identity keys. And one of the nicest features of noise protocol is that it has formal proofs for confidentiality and authentication security guarantees for all of the patterns that it provides. And there is a very nice tool called Noise Explorer, which you can open and actually download those formal proofs. But let's take a look at the example of how exactly noise protocol works. And we'll take a look at the pattern which uses static keys for both of the participants. So in noise, the client side is often called the initiator, and the server side is called the responder. Here, you are expected to have the static keys already exchanged between the client and the service. And for this, you can either use an existing PKI, or you can pre-distribute your keys in the application. Then, when the handshake starts, the initiator generates an ephemeral key pair, and then performs a Diffie-Hellman key operation on the keys that it knows. And an important note here is that the notation, this official notation of noise, doesn't mean that it actually sends the results of Diffie-Hellman key agreement. It just shows you the order of operations. Generate an ephemeral key, and perform 2 Diffie-Hellmans. And the responder also generates an ephemeral key pair and performs 2 Diffie-Hellman operations on its side as well. And in the end, when we combine the results of those operations, we also weight in the nonces, and we also weight in the hash of the whole handshake. We get a symmetric key, which we can later use to establish a secure channel. And how can we switch between different patterns? We can just add or remove keys. And in this case, for example, we can remove the identity key of the initiator. And what we'll end up with is a protocol in which you will only verify the identity of the server. And how you change the handshake is you just remove the corresponding Diffie-Hellman key agreements that involve this key. And for example, let's now remove all of the static keys, and we'll still end up with a valid protocol with a completely ephemeral handshake. So this is roughly how noise protocol works, and now I'll give this presentation to Katya, who will tell you exactly how we combine noise protocol with remote attestation.
As I described, now we have the handshake that allows us to establish a secure communication channel. Now we need to bind it to the attestation. And what we wanted to do is we wanted to mess as little as possible with noise, because as Ivan has described, it's a nice minimalistic protocol. It has formal security proofs. We didn't want to mess with that at all. Which meant that we wanted attestation to be a separate step. We also needed to be able to adapt our solution to the case of bidirectional attestation for the situation when it is two enclaves communicating, or when the client can provide some sort of attestation from their end. Also, there are use cases where supporting multiple attestation is also beneficial. So we wanted to accommodate all these use cases. Next slide, please. What you see now is the noise protocol with just the ephemeral key, as I described, to which we have added a unidirectional attestation step. So now responder attests itself to the initiator. What happens is the initiator is sending the request, the responder sends back the evidence, and what we require is that this evidence contains the binding key, which will be signed by the rest of the evidence. And then we perform the noise and N handshake as usual. And at the end of that handshake, we get the handshake, the shared handshake hash, which both initiator and the responder will possess. So what we do now is we sign this handshake with this binding key, allowing the initiator to establish that the attestation and the handshake happened with the same party. And by the way, this is not our invention. It is a part of specification of the noise protocol, that by the end of the handshake, you get both the encryption key and the handshake hash, which you can use specifically for binding. So by appending the signature, we bind the attestation to the handshake. Now, this might not be like the theoretically perfect solution. If it was possible in all cases to run attestation, to provide attestation in such a way that it will sign the handshake hash directly, it would be preferable for multiple reasons. In particular, it would establish freshness of the attestation. Our solution doesn't get that for practical reasons, because the hardware platforms that we want to support not always support attestation of arbitrary data on demand. In this way, we create a proxy by signing just the binding key, but still allowing to establish the continuity of the communication. Next slide, please. This scheme can be scaled really nicely to the bidirectional attestation. All that needs to happen is that initiator now sends their own evidence with the request, and both parties use binding keys from that they included in the evidence to sign the handshake hash. So the only thing that changes in the protocol is that now initiator has to sign yet another message with the signed handshake hash, and the channel is not open until that happens, until responder receives and verifies the signature. Next slide, please. Scaling to the multiple attestation is also straightforward. So each attestation, if you have multiple attestations, you want to include its own separate binding key with each of the evidence, and then you sign the handshake hash with all of them. So in this case, if your system has multiple attestation components, you can verify all these attestations together and bind them all to the session. Next slide, please. So now we come to our conclusion. To reiterate, our use case really emphasizes minimizing of the TCB. This was the major factor in picking the noise protocol. And that's why we picked the noise protocol framework, because it's minimal and because it's so flexible. So it can include support authentication or not support authentication, depends on what you want. And we have found a way to bind our pre-existing approach to the attestation to the noise handshake. If you're curious to learn more, please check the links. Project Talk is all on GitHub, all open source. And if you're curious to look into the code, here are some pointers. And thanks for your attention.